In this recording, we'll discuss the types of collision that we usually consider when studying momentum. The collisions we study are usually broken in two types. What we call elastic collisions. They are the ones that do not result in energy losses. And inelastic collisions, the ones that result in energy losses. Remember, the overall energy is preserved, is conserved, but energy of the system can diminish, and that's what we mean by energy losses. Like those objects that are interacting will end up with less energy than what they had initially, so then they have an energy loss. Now, the key point is, that's very important, that what we have in big here in bold, in either case, in all types of collision, momentum is conserved. That's the key. Momentum is going to be always conserved. Now, just a reminder of the definition of kinetic energy. It's the energy associated with motion. Whenever we have motion, we are going to have kinetic energy. It's 1/2 of mv squared. Now, when something has momentum, it's going to necessarily have a kinetic energy, because it has momentum, it has a velocity and a mass. Both of them figure into the kinetic energy expression. Now, what we call elastic collisions. In elastic collisions, you see it in red. Momentum is conserved. We need to remember that. It's always conserved. But then also kinetic energy is conserved. Okay? So, for elastic collisions, we have two things that are conserved. Momentum and kinetic energy. What does that mean? Okay, if my system is made up of two objects, the overall momentum of the system is the momentum of object 1 plus momentum of object 2. What we are saying, by saying momentum is conserved, that momentum of the system is going to remain constant. Now, in addition to that, the kinetic energy of the system is going to be kinetic energy of mass 1 plus kinetic energy of mass 2. That sum is going to also be conserved. Now, just while writing this, just a few reminders. Remember, the top one is a vector. It has arrows on top of it. Direction is important. The bottom one is a scalar. Direction is not important. Here you are going to add up the kinetic energies no matter what. Here, the direction is going to make some of the momenta positive and some of the momenta negative. Let me put it some other way. For example, if I have two equal masses moving towards each other with the same speed, their overall momentum is 0. But their overall kinetic energy is not going to be 0, because kinetic energy is not going to depend on the direction, while momentum depends. Okay. When are we going to have elastic collisions? In real life, almost never. It happens like at the particle level, like what we have here is a drawing coming out of a particle accelerator kind of experiment. Now, but in real life, elastic collisions are not really existent. Something that's close to elastic are billiard balls hitting each other. Now, whenever things are going to collide without losing energy, it's an elastic collision. But then in billiard balls, for example, when they collide, you hear a sound. The fact that you hear a sound tells you there must be some of the energy that they had, some of the kinetic energy that they had, is going to be transformed into sound energy. That's why we heard it. Now also, heat. Whenever they hit each other, both of them are going to heat up. Now let's see if I can pull it out here. Wow, I got the number correct. This I meant to have it actually in the other lecture, the lecture about energy, but anyway, so I put it up here. this is something that the teacher source sells. It's actually two large spheres, metallic spheres, and the idea is you take the spheres and hit them against each other. So hold one at each hand and hit them against each other. And you can put a piece of paper in between. And what you will find out when you hit them against each other with a piece of paper, you get the paper to burn. So just a way to illustrate that some of the kinetic energy that they had before they hit each other is going to be converted into heat. Okay, so that's a very neat demonstration for that. Okay, now even though elastic collisions are rare in real life, we usually approximate a lot of collisions to elastic collisions. We say, assume that the collision is elastic. That's one keyword you need to look for in questions. Do they tell you it's an elastic collision? Okay, in elastic collisions, objects are going to move apart of each other. They are going to move apart of each other after the collision. They are not going to stick. That's another thing to pay attention to. Now, in non-elastic collisions, we call it inelastic collisions. Okay, we have only one thing that's conserved: momentum. Kinetic energy is not conserved. We don't deal with it. So actually, it's the easier one to deal with mathematically because we have one equation to contend with. Of course, this equation depends on direction, but it's one equation. Only momentum is conserved. Again, elastic collisions, both momentum and kinetic energy is conserved. Inelastic collisions, only momentum is conserved. Now, explosions, for example, are going to be inelastic collisions. Things that hit and crumble together are inelastic collisions. Some of the energy of motion is going to be transformed into heat, into spring potential energy in crumbling the matter of the materials. For example, car collisions, when they get destroyed, some of that kinetic energy is going to go into compressing the material of those cars. So it's some type of a spring potential energy that's going to be stored in that material. So those cases, whenever kinetic energy is not conserved, it is an elastic collision. Now, whenever we are going to have to solve a problem involving momentum, okay, first, how are we going to determine if a problem is going to involve momentum? Usually, when you have more than one mass, more than one object interacting, where we can identify a before and after situations. And one good thing to do is to make a drawing, an illustration of what's happening before and what's happening after. And then we check if we have external forces or not. If we have external forces, that's going to be a little problematic, and maybe we cannot use conservation of momentum then. And then what we do, we calculate the momentum before, or we write expressions for momentum before. And we write expressions for the momentum after. Okay, if it is known, if everything is known, we calculate it. If it's not known, we just write expressions for it. And then we set them equal to each other and solve for whatever is needed.